So we have here a structure composed by two bars, a column and a beam, subject to uniform load of 8 kilonewtons per meter applied only to the beam. The objective is to compute the internal forces. So let's start with the reactions. This is a full clamped or fixed support, so it does have all three reactions: a vertical, an horizontal, and a moment. Using the usual convention, we get sum of horizontal forces. We only get AX, so AX is 0. Sum of vertical forces, we have AY and minus this distributed load, 8 times 4, which results in AY equal to 32 kilonewtons. Sum of moments to A, this one causes no moment, this one causes no moment, this one causes a positive moment, and this one causes a negative moment. Minus 8 times 4, which is a resultant, times 2, which is the distance. So AM is equal to 64 kilonewtons meter. So representing that, here we have our structure, the load. This is 4 meters. This is 5 meters. Fully clamped. The reaction is 32 kilonewtons and 64 kilonewtons meter. For internal forces, this is the convention we have assumed. This bar goes from the left to the right. This bar goes upwards, meaning this is the left, this is the right. So let's go and draw the diagrams for this structure. This can be axial, shear, moment. So starting with the axial force, if I calculate all the forces parallel to the bar to the left of this section, I have this force of 32, which is compression, meaning negative 32. That there's nothing along the bar that is applied parallel to the bar, so it means this diagram is constant, equal to 32. Let's stop here and we'll look at the beam later on. If we look at shear, if you look to everything to the left of the green section, there's nothing. And if I keep moving along this column, there's no forces perpendicular to the bar, meaning that shear is 0 all the way across. If I look at now let's leave the beam for later. If I look at bending moments, to the left of the green section, the only bending moment I have is this 64. 64 is negative. It causes tension on the upper side. And I do know that dm dx is equal to minus v. Since shear is 0, it means moment is constant. So I can draw it like this. Constant. Now I need to go to the second bar, to the beam. And one way of calculating the internal force at the beam is to look to the sum of everything to the left of the green section. Another alternative is to isolate this node. So let's isolate the node. So this is the left, this is the right, this is the left, this is the right. On the column I already calculated the internal forces. I have a force of 32 of compression, and I have a bending moment like this, which is worth 64. When it comes to the beam, I don't really know, so I'm going to assume everything is positive. I'm going to assume I have a normal force, a bending moment, and a shear. And now, in order to guarantee equilibrium of this node, I can compute these three internal forces. So just for simplicity, let's move this a little bit to the side. Done. So if I look at sum of vertical forces, I get 32 plus V equal to 0, comes V equal to minus 32. Sum of horizontal forces, I have nothing here, so I get N, which must be 0. If I look at moments, since this distance is very small, this distance is very small, I only have the moment, so 64 plus M, which means M is equal to minus 64 kilonewtons meter, kilonewtons. So let's go back to the diagrams. The axial force here, based on this, is 0. I have no forces along the bar changing it, so it remains 0. Shear is minus 32, so 32 on the negative side, and then I have a force, a constant distributive force pushing it down. And so, since the distributive force is constant, it means the shear is linear, and it's worth 8 times 4, 32, it goes from 32, it goes down 32, ends in 0. The moment is minus 64, and since this one is linear, this is parabolic, big slope at the beginning, 0 slope at the end, and the change is the area of this, 32 times 4 divided by 2, the area of the triangle, 64, it comes from 64, it goes all the way to 0.